Ma'am, good evening, ma'am.
Good evening, sir.
Yes, ma'am. Ma'am, can you hear me? Hello? 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 Right. Good evening. Yesterday, we were learning about the basics introduction to the chapter surface chemistry, and we learned few terminologies in surface chemistry, and we learned a lot of questions based on the basic concepts of the surface chemistry, adsorption concept in specific. We learned the difference between adsorption, absorption. We learned the difference between physical adsorption, chemical adsorption, with examples we have learned in detail yesterday. Now, adsorption isotherms. Adsorption isotherm, it's a mathematical equation which describes the relationship between pressure of the gaseous adsorbate and the extent of adsorption at fixed temperature. So a mathematical equation which describes the relationship between pressure of the gaseous adsorbate and the extent of adsorption at a fixed temperature is called as adsorption isotherms. The extent of adsorption is expressed as mass of adsorbate adsorbed on 1 unit of adsorbent. So mass of adsorbate adsorbed on 1 unit mass of adsorbent. We learned in the previous class, adsorbate is something which gets adsorbed. Adsorbent is a chemical substance which provides the surface area for adsorption. In chalk and dust, chalk particles will be called as adsorbate and the duster will be called as adsorbent. All right. So extent of adsorption is expressed as mass of adsorbate adsorbed on 1 unit mass of the adsorbent. If X grams of adsorbate is adsorbed on M grams of adsorbent, so mass of adsorbate is X, the mass of adsorbent is M, then the extent of adsorption is equal to X by M. So X is mass of adsorbate and M is the mass of adsorbent. So the extent of adsorption at a fixed temperature. So the relationship between the pressure and the extent of adsorption at a fixed temperature is called as adsorption isotherm. Various adsorption isotherms are commonly employed. The first one is Freundlich adsorption isotherm. This Freundlich adsorption isotherm you have in the syllabus. What is the Freundlich adsorption isotherm? Freundlich adsorption isotherm is obeyed by adsorptions when adsorbate forms monomolecular layer on the surface of the adsorbent. So Freundlich adsorption isotherm, the condition for Freundlich adsorption isotherm is the adsorbate should form a monomolecular layer on the surface of the adsorbent. So X by M, X is mass of the adsorbate, M is the mass of adsorbent, that is equal to K into P to the power 1 by N. So X by M is equal to K into P to the power 1 by N. So this is the mathematical representation of Freundlich adsorption isotherm. X by M is equal to K into P to the power 1 by N. X is mass of adsorbate, M is mass of adsorbent, K is a constant, P is pressure, N is also a constant here. So for this equation, when you take log on both the sides, we can write it as log X by M is equal to log K. This is in 2. This K is one term, the P to the power 1 by N is another term. So log K plus 1 by N log P. So log a to the power b, log a to the power b can be written as b log a. So p to the power log of p to the power 1 by n can be written as 1 by n log p. So that's how we have written here. Log x by m is equal to log k plus 1 by n log p, where x is the weight of the gas adsorbed by m gram of the adsorbent. In simple words, we can write x is the mass of adsorbate and m is the mass of adsorbent. P is the pressure. Thus, x by m represents the amount of gas adsorbed by the adsorbent per gram unit mass. K and n are constant at a particular temperature, and for a particular adsorbent and adsorbate gas, n is always greater than 1. N is always greater than 1, indicating that the amount of gas adsorbed does not increase as rapidly as pressure. Indicating that amount of gas adsorbed does not increase as rapidly as the pressure. So Friedrich adsorption isotherm, we know mathematical representation, x by m is equal to k into p to the power 1 by n. Taking log on the both the side also I gave. Now the conditions at low pressure, the extent of adsorption varies linearly with pressure. At low pressure, the extent of adsorption varies linearly. That is, x by m is proportional to p at low pressure. So at high pressure, it becomes independent of pressure. So x by m is proportional to p to the power 0. It does not depend on the pressure. At moderate pressure, x by m depends upon the pressure raised to the powers. X by m is proportional to p to the power 1 by n. So you can see this at low pressure, x by m is directly proportional to the pressure. So you can say at low pressure, as the pressure increases, the amount of this ratio, x by m ratio, also increases. At high pressure, the x by m is independent of p to the power 0 is 1. So anything to the power 0 is 1. That means x by m is independent of the pressure at high pressure. At moderate pressure, x by m is proportional to p to the power 1 by n. Now, when we say x by m is proportional to p to the power 1 by n, if we remove the proportionality sign, we give x by m is equal to k into p to the power 1 by n. This is called as Friedrich adsorption as the mathematical representation. So the same graph, when we take log and plot it, log x by m on the y-axis and log p on the x-axis, we get a straight line. The straight line, the slope of the straight line corresponds to 1 by n. The slope of this line corresponds to 1 by n. So we learned here x by m is equal to k into p to the power 1 by n. So taking log on both the sides, we write log x by m is equal to log k plus 1 by n log p. This 1 by n is nothing but, in graph, we get it as a slope. And this intercept is log k. This value is log k. This equation in the form of y is equal to mx plus c. So a straight line. So this is the graphical representation of Friedrich adsorption isotherm. The next what we have is Langmuir adsorption isotherm. This Langmuir adsorption isotherm we do not have in this syllabus, but we'll try to just make one or two statements on Langmuir adsorption isotherm. One of the drawbacks of Friedrich adsorption isotherm is that it fails at high pressure. Langmuir adsorption isotherm is applicable only for low pressures. At high pressure, it clearly says x by m is independent of pressure. So Friedrich adsorption isotherm fails at high pressure. So Irving Langmuir in 1916 derived a simple adsorption isotherm. On theoretical consideration. Based on kinetic theory of gases, and this is named only till the whole surface is completely covered with unimolecular layer of the adsorbed gas. So once the layer is completely adsorbed by air, yes, blue line corresponds to the adsorbent. Absorption takes place. This orange color shows that adsorption of the adsorbate. Adsorption takes place on the surface of the solid. Covered. So once the whole surface is completely covered, so adsorption consists of two opposite, namely condensation of gas molecules on the solid surface and evaporation. Evaporation is desorption. So when gas gets accumulated in the solid, it means it's condensation. Likewise, this gas molecule also can vaporize, that's called as desorption, evaporation from the surface. So these are the two forces, opposing forces acting. The rate of condensation depends upon the uncovered bare surface of the adsorbent. If the uncovered layer is there, if some more space is there, condensation will be more. Naturally, at start, when whole of the surface is uncovered, the rate of condensation is very high. As the surface is covered more and more, the rate of condensation progressively decreases because the molecules are getting adsorbed. Therefore, condensation progressively decreases. On the contrary, the rate of evaporation depends upon the covered surface and hence increases as more and more of the surface is covered. Evaporation will increase as more and more of the surface is covered. Ultimately, an equilibrium will set up at a stage. Rate of condensation becomes equal to rate of evaporation. It is called as adsorption equilibrium. The rate of condensation also depends upon the pressure of a gas, since according to kinetic theory of gas, the number of molecules striking per unit area is proportional to pressure. So the mathematical representation of Langmuir adsorption isotherm is X by M is equal to AP divided by 1 plus BP, where A and B are constants and the value depends upon the nature of the adsorbate, nature of the gas, that is adsorbate, nature of the solid, adsorbate, and the temperature. A and B are constant. It depends on the nature of adsorbate, nature of adsorbent, and also temperature. Their value can be determined from experimental data. Langmuir adsorption isotherm we do not have in the syllabus, but just remember. Adsorption from solution. Before that, Langmuir theory of unimolecular adsorption is valid only at low pressure and high temperature. This is a limitation of Langmuir's adsorption. When the pressure is increased or temperature is lowered, additional layers are formed. This has led to a modern concept of multi-layer adsorption. It has led to the modern concept of multi-layer adsorption. Next is adsorption from solutions. We were talking henceforth with the gases. Now adsorption from solution. The process of adsorption can take place from solution also. Adsorption can take place from solution also. In any solution, there are two or more components. That is, a solution is made of what? Solute and a solvent. So you have two or more components. The solute may be present in molecular or ionic form. The solute may be present in molecular or ionic form. In case of glucose solution, glucose is the solute, water is the solvent. Glucose, when put in water, it dissolves and remains as glucose molecules itself. But in NaCl, if you take sodium chloride, the salt, if you put sodium chloride in water, sodium chloride will dissociate to form Na plus and Cl minus. Therefore, it remains as ions. The extent of adsorption from solution depends upon the concentration of the solute in the solution. And hence, it can be expressed by Freundlich isotherm. The Freundlich isotherm for adsorption from solution is X by M is equal to K into C to the power 1 by N. C stands for concentration. So in case of pressure, we write X by M is equal to K into P to the power 1 by N. Here, in case of solution, X by M is equal to K into C to the power 1 by N. C stands for concentration. All the other factors remains the same. So the plot of X by M against concentration is similar to that of Freundlich adsorption isotherm. The above equation may be written of the following form. So taking log on both the sides, x by m is equal to k into c to the power 1 by n. So if we take log on both the sides, we can write log x by m is equal to log k plus 1 by log c, where c is the equilibrium concentration. Now, we'll learn some of the questions based on Freundlich adsorption isotherm, and then we will go for the concept called as catalysis. Now, this is what you're supposed to know with respect to adsorption. The questions what we learned yesterday and what we're going to learn today. Based on those questions, they can ask you some of the questions in the exams. In adsorption of a gas on the solid, adsorption of gas on the solid, gas is the adsorbate, solid is the adsorbent. Freundlich isotherm is obeyed. Freundlich isotherm is obeyed. The slope of the plots is 0. The slope of the plots is 0. Thus, the extent of adsorption is directly proportional to pressure of the gas, inversely proportional to pressure of the gas, independent of the pressure of the gas, proportional to the square of the pressure of the gas. We know Freundlich adsorption isotherm, x by m is equal to k into p to the power 1 by n. Taking log on both the sides, we can natural log, if you take natural log of x by m is equal to natural log of k plus 1 by n, 1 by n. One by n log of p. Now, thus we can write x by m is equal to k into p to the power 0. Why we can write p to the power 0? Because they have clearly given the slope of the plot is 0. That is 1 by n is 0. Slope is 0. When slope is 0, this factor becomes log p to the power 0. We can write as k into p to the power 0. Thus, we can write x by m is equal to k. Hence, we can say adsorption of gas on the solid, Freundlich adsorption isotherm is obeyed. The slope of the plot is 0. Thus, the extent of adsorption is independent of pressure of the gas. It does not depend on the pressure because it becomes p to the power 0. 1 by n is 0. So directly, instead of taking log, we can directly write x by m is equal to k into the p to the power 0. So it becomes what? X by m is equal to k. So it is independent of the pressure of the gas. The second question. In Freundlich adsorption equation, x by m is equal to k into p to the power 1 by n. Then the value of n is always greater than 1, always smaller, always equal to 1, greater than 1 at low temperature, and smaller than 1 at high temperature. So x by m is always greater than 1 in Freundlich adsorption equation. The next question. In Freundlich adsorption isotherm, the value of 1 by n is between 0 and 1 in all cases, between 2 and 4 in all cases, 1 in case of physical adsorption, 1 in case of chemical adsorption. We know that x by m is equal to k into p to the power 1 by n. We know x is the mass of adsorbent, m is the mass of adsorbate. And also we know that value of n is always greater than 1. So the value of 1 by n is between 0 to 1 in all cases. So the value of 1 by n, so it's between what? 0 to 1. So hence the answer for this question is option A. The next question, for adsorption of gas on a solid, plot of x by m versus log x by m versus log p is linear. with a slope equal to, we learned it. X by m is equal to k into p to the power 1 by n. When we take log on both the sides, it will be log x by m, that will be equal to log k plus 1 by n log p. So when we plot a graph, log x by m as a function of log p, we get a straight line like this. And this is called as intercept. And this intercept gives you the value of log k. And if you take the slope will be equal to 1 by n. We learned this. Hence, the answer for this question is option D. The plot of log x by m versus log p is linear with the slope equal to 1 by n. The next question. At low pressure, the fraction of the surface covered follows zero order reaction, first order reaction, second order reaction, or fractional order reaction. As we know, x by m is equal to k into p to the power 1 by n. At low pressure, x by m is proportional to p. It's directly proportional to the pressure. We have learned the graph. Thus, it clearly indicates the reaction is a first order reaction because adsorption is directly proportional to P. Hence, it is clearly shows it's a first order reaction or first order kinetics. Hence, the answer will be option B. The next question, adsorption of gas on a surface follows Freundlich adsorption isotherm. Adsorption of a gas on a surface follows Freundlich adsorption isotherm. Plot of x by m versus log p gives a straight line with a slope equal to 0.5. Then x by m is the mass of gas adsorbed per gram of adsorbent. Now, they clearly say, we know that log x by m is equal to log k plus slope is 0.5. When I say slope is 0.5, we can write this equation as log x by m is equal to log k plus 1 by 2 log p. 0.5 can be written as 1 by 2. So, or from this, we can come to the conclusion x by m is equal to k into p to the power 1 by 2. K into p to the power 1 by 2. From this, we understand that adsorption is proportional to square root of pressure. Square root of pressure. P to the power half. P to the power half can be written as square root of pressure. Hence, the answer for this question is adsorption is proportional to the square root of pressure. It is option B. The next question. For a linear plot, x by m versus log p in Freundlich adsorption isotherm, which of the following statement is correct? X and n are constants. For the Freundlich adsorption isotherm, we know log x by m is equal to log k plus 1 by n log p for the Freundlich adsorption isotherm. Now, comparing this equation with y is equal to mx plus c, comparing this equation with equation y is equal to mx plus c, we can write slope m is 1 by n and the intercept is c, that is log k. So answer for this question is option C. Only 1 by n appears as a slope. Answer C. The next question. As gas undergoes physical adsorption on the surface and follows the given Freundlich adsorption equation, x by m is equal to k into p to the power 0.5. X by m is equal to k into p to the power 0.5. The adsorption of the gas increases with decrease in pressure, increase in temperature, decrease in pressure and decrease in temperature, increase in pressure and decrease in temperature. Adsorption of gas increases with increase in pressure, and generally adsorption decreases with increase in pressure. Remember, generally adsorption, where is it? Adsorption increases with increase in pressure and adsorption decreases with decrease in temperature. Hence, the answer for this question is option C. The next question, which of the following is not the property of physical adsorption? Which of the following is not the property of physical adsorption? Unilayer adsorption occurs. Greater the surface area, more adsorption. Lower the temperature, more the adsorption. Higher the pressure, more the adsorption. So physical adsorption is a multi-layer. It is a multi-layer. So here they said, which is not the property of the physical adsorption. So unilayer adsorption occurs. It is not the property of the physical adsorption. Hence, the answer is option A. The next question. Application of adsorption. Application of adsorption is completely theoretical. The phenomenon of adsorption finds number of applications. Important application are as follows. The first one, production of high vacuum. Now, when we say production of high vacuum, so in removal of moisture and other gases, adsorption can be used, applicable. Next, in gas masks, we have been learning from yesterday the application of adsorption as with the example of gas masks. Gas mask, this apparatus is used to adsorb poisonous gases like chlorine, carbon monoxide, oxides of sulfur, that sulfur dioxide, sulfur trioxide, etc., and thus purify the air for breathing. So gas mask will adsorb the poisonous gases and purify the air for breathing. Third application for desiccation or dehumidification. These substances can be used to reduce or remove water vapors from moisture present in air. So that's called as desiccation. To removal of moisture from air is called as desiccation. Silica gel and alumina are used as dehumidification in electronic equipments. Silica gel, you have observed silica gel sachets whenever you buy some electronic equipments to remove the moisture present in air. They keep silica gel sachets near the apparatus. Next, removal of coloring matters from solution. Coloring matters. Oil is yellowish in color, but we have something called as refined oil. In refined oil, the color is removed. The color is removed by using animal charcoal. Animal charcoal removes color of the solution by adsorbing coloring impurities. Animal charcoal is also used to decolorize in the manufacturing of cane sugar. Sugar is white in color, but sugarcane juice is greenish in color. So to remove the color of the sugar present in the sugar, they use animal charcoal. And most important application of adsorption is heterogeneous catalysis. Now, mostly heterogeneous catalytic reaction proceeds through adsorption of gaseous reactants on solid catalyst. So reactants are in gaseous state and catalyst is in solid state. Example for we'll be learning heterogeneous catalysis in the next topic, catalysis. Finally, powdered nickel is used for dehydrogenation of oil. Finely divided vanadium pentoxide is used in the contact process. So this is all heterogeneous catalysis. Reactants and catalyst are in different phase, or different states. When the reactant and catalyst are in different states or different phases, then we call it as heterogeneous catalysis. The next is separation of inert gases. So inert gases can be separated. So inert gases, noble gases, are present in the atmospheric air in very less quantity. They are made to adsorb on the charcoal, and the mixture of inert gases can be separated by adsorption on coconut charcoal at different low temperatures. So coconut charcoal is used to separate a mixture of noble gases. So again, to separate the mixture of noble gases, the principle used is adsorption. The seventh application is softening of hard water. Hard water is because of the presence of calcium and magnesium salts. So hard water will not give lather with the soap. The hard water is made to pass through column packed with zeolites. So when hard water is passed through column packed with the zeolite, zeolites are sodium aluminum silicates. Calcium and magnesium ions, which are responsible for hardness, gets adsorbed on the zeolite, exchanging sodium ions. See, this is sodium aluminum silicate. If water contains calcium chloride, this calcium chloride will adsorb on the zeolite to form calcium aluminum silicate, and the sodium ion will get into the solution. Therefore, hardness of the water will be removed. So these are the applications of adsorption. So many applications we have learned, 7, 8 applications. So we have few more. The exhausted zeolite is regenerated with 10% sodium chloride. So this zeolites, sodium aluminum silicates, can be regenerated. Deionization of water. Water can be deionized by removing all the dissolved salts with the help of cation and anion exchange resin. So this is also based on the principle adsorption, deionization. D stands for removal. Removal of all any ions present, whether it's a cation or anionic ions present in water, is called as deionization. In curing diseases, a number of drugs are adsorbed on the germs and kill them, or these are adsorbed on the tissues and heal them, not heal them. Heal them, curing disease by the process of adsorption. Cleansing agents, soaps and detergent gets adsorbed on the interface and thus reduce the surface tension between dirt and cloth. Subsequently, the dirt is removed from cloth. Froth flotation, low-grade sulfide ore is concentrated by separating it from silica and other earthy matters. This you will be learning in second PUC, 12th standard. Adsorption indicators, surface of certain precipitates, such as silver halides, have the property of adsorbing some dyes like eosin, fluorescein. So adsorption is used also as an indicator. Chromatographic analysis. Chromatography is a separation technique. It's an instrumentation process. The phenomena of adsorption has given an excellent technique of analysis known as chromatographic analysis. In dyeing, coloring, many dyes get adsorbed on the cloth, either directly or by the use of mordants. So these are the applications of adsorption. You can just go through the application of adsorption for a minute or so, and we'll continue with the catalysis topic after a few minutes. Just to have a look at the applications. So many applications we have learned. They can ask you, mention few of the applications of adsorption. So You can mention few. So many we have learned, and 13, 14 applications we have learned. So you can mention few. The next one. The next topic is catalysis. This chapter is easy, and we have finished 1/3 of the chapter, that is adsorption. You have to learn catalysis and colloids. Catalysis is also a very small topic. Catalyst. What is a catalyst? A catalyst is a chemical substance which alters the speed of the chemical reaction, which alters. When we say which alters, it can either speed up or speed down. It can either increase the rate or decrease the rate of a reaction without itself being used up. That's the definition of catalyst. A catalyst is a chemical substance which alters the chemical reaction rate without being used up. Berzelius in 1836 introduced the term catalysis and catalyst. Oswald in 1895 redefined the catalyst as a substance which changes the rate of a reaction without affecting the overall energetics of the reaction is termed as a catalyst, and the phenomenon is known as catalysis. So simply we can understand the definition of catalysis as, or how do you define a catalyst is any chemical substance which can alter the rate of a reaction, which can either decrease or increase the rate of a reaction, can be called as a catalyst. And the phenomenon is called as catalysis. We have two types of catalysis. It is a two-marker in any one of them can be asked amongst the types of catalysis. The first one is homogeneous catalysis. Homo stands for same. What is homogeneous catalysis? A catalytic reaction in which the reactants and the catalyst are in same phase. When the reactant and the catalyst are in same phase, then we call those kind of the reactions as homogeneous catalytic reaction. Now, for an example, lead chamber process. Lead chamber process. Sulfur dioxide is a gas, oxygen is a gas, and nitrogen dioxide is also a gas. Nitrogen dioxide is a catalyst. So reactants and the catalyst both are in gaseous state. Since the reactant and catalyst are both in the gaseous state, it will be an example for homogeneous catalysis. Hydrolysis of an ester. Ester is a liquid, water is a liquid, formaldehyde is also a liquid. So hydrolysis of ester in the presence of formaldehyde is also an example for homogeneous catalysis. Homogeneous catalysis is a catalytic reaction in which the reactants and the catalyst are in same phase. The next is heterogeneous catalysis. A catalytic process in which the reactants and the catalyst are in different phase, or different state. Those are called as heterogeneous catalysis. Heterogeneous catalysis or catalytic reactions in which the reactants and the catalyst are in different phase. In contact process for the preparation of sulfuric acid, sulfur dioxide is a gas, oxygen is a gas, platinum is a solid, or we can use vanadium pentoxide. This is also a solid. So your reactant and the catalyst are in different phase. When the reactant and the catalyst are in different phase, then we call those kind of reactions to be an heterogeneous catalysis. Likewise, one more example, synthesis of ammonia by Haber's process. Nitrogen is a gas, hydrogen is. So reactants and the catalyst. Reactants are gaseous state, the catalyst is in solid state. When the reactants and the catalyst are in different states, then we call those kind of catalytic reaction as heterogeneous catalysis. Now, few more terminologies we have to understand. In modern day, we do not call as positive catalyst and negative catalyst. So catalyst, and they use another term called as inhibitor. Catalyst will increase the rate of a reaction, and inhibitor will decrease the rate of a reaction. In the old terminology, a catalyst is classified into two, that is a positive catalysis and a negative catalysis. So when the rate of a reaction is accelerated by a foreign substance, when the rate of reaction is increased by a foreign substance, it is said to be a positive catalyst. And the phenomenon is known as positive catalysis. Now, for an example, decomposition of potassium chlorate. Potassium chlorate is a solid. This potassium chlorate, when you heat it to 270 degrees in the presence of manganese dioxide, so the decomposition of potassium chlorate will increase. Therefore, this reaction will be called as positive catalysis. Now, one more example, oxidation of sulfur dioxide to sulfur trioxide in the presence of vanadium pentoxide is also an example for positive catalysis. So chemical substances which increases the rate of a reaction is called as positive catalysis. Negative catalysis. These are certain substances, when added, the reaction mixture retards the reaction rate. Retards means slows down the reaction. So chemical substance which slows down the speed or the rate is called as a negative catalysis. Example for negative catalysis, oxidation of sodium sulfite to sodium sulfate in the presence of an alcohol. Benzaldehyde is oxidized to benzoic acid in the presence of diphenylamine. Tetraethyl lead is added to petrol to retard the ignition of petrol vapors on compression in an internal combustion engine, and thus minimize the knocking effect. Knocking effect. We will be learning the knocking effect in your engineering classes. The next is autocatalysis. A reaction, in a certain reaction, one of the product itself acts as a catalyst. Then those kind of reactions are called as autocatalysis. Now you will have done a titration of potassium permanganate versus oxalic acid. Titration of oxalic acid versus potassium permanganate. During the course of titration, what happens when you titrate potassium permanganate into oxalic acid? Manganese ions will be formed. These manganese ions itself will behave like a catalyst. So those kind of catalytic reactions are called as autocatalysis. Autocatalysis means a reaction. In a reaction, one of the product of the reaction will itself behave like a catalyst. Those are called as autocatalysis. The next one, see, this is the same equation. Induced catalysis. When one reaction influences the rate of other reaction, which does not occur under ordinary condition, the phenomenon is known as induced catalysis. When one reaction influences the rate of other reaction, which does not occur. Example, sodium arsenide solution is not oxidized by air. If, however, air is passed through a mixture of solution of sodium arsenide and sodium sulfite, both of them undergo simultaneous oxidation. So, individually, sodium arsenate cannot be oxidized by air. But however, the mixture of sodium arsenite and sodium sulfite, when exposed to atmospheric air, they undergoes oxidation simultaneously. That means the oxidation of sodium sulfite induces the oxidation of sodium arsenide. Those are called as induced catalysis. Acid-base catalysis. According to Arrhenius and Oswald, H plus and H minus ion acts as a catalyst. OH minus. So ester, hydrolysis of ester in the presence of an acid, H plus indicates acid, or base OH minus is an example for acid-base catalysis. So acid can catalyze the reaction, or the base also can catalyze the reaction. So these 6 or 7 types of reactions we learned, types of catalysis we have learned. Now we are supposed to learn the characteristics of the catalyst. Now, catalysis. The following are the characteristics which are common to most of the catalytic reactions. A catalyst remains unchanged in mass and chemical composition at the end of the reaction. So catalyst will take part in the reaction, but at the end of the reaction, catalyst remains same or unchanged in the mass and also the chemical composition. For an example, if we take the decomposition of potassium chlorate to give potassium chloride and oxygen oxide. So the amount of manganese oxide used during the process remains the same at the end of the process. Not only the amount, the chemical composition also remains same, but the physical texture might have been changed. The physical character might have changed, but the chemical character and the amount remains same. This is the first property of the catalysis. The second, a small quantity of catalyst is enough to bring about the chemical reaction. So if you take 2 grams of potassium chloride, around 0.4 grams of manganese dioxide is enough. So catalysts are generally small quantity. Small quantity of catalyst is enough to bring about the catalytic reactions. They can ask you mention the characteristics of catalyst for 3 marks. So remember. Third is example I have given you, a small quantity. Here they have given a different example. All right. Example. The third property, catalyst cannot start the reaction. The catalyst cannot initiate the reaction. The function of the catalyst to alter the speed of reaction rather than to start. It can alter the reaction when the reaction is taking place, but it cannot start the reaction. The next one, the catalysts are generally specific in nature. There is nothing called as universal catalyst. So catalysts are highly specific in nature. A substance which acts as a catalyst for a particular reaction fails to catalyze the other reactions. Therefore, catalysts are generally specific. The next one is catalyst cannot change the position of the equilibrium. Catalyst cannot change the position of the equilibrium. We have 2 more concepts to be learned in catalysis. That is catalytic promoter and catalytic poison. Now, for an example, if you take this reaction, nitrogen and hydrogen giving you ammonia. Here, iron is used as a catalyst. The efficiency of iron can be increased by adding molybdenum. Molybdenum behaves like a catalyst for iron. That means molybdenum will increase the activity of iron. So any chemical substance which increases the activity of a catalyst is called as catalytic promoter. So example for catalytic promoter I've given you. There are explanations here. Now similarly, catalytic poison, when we say any chemical substance which decreases the efficiency of a catalyst will be called as catalytic poison. Now, arsenic oxide, traces of arsenic oxide in the reacting gases reduces the activity of platinized asbestos, which is used as a catalyst in the contact process. In the contact process, sulfuric acid preparation, platinum can be used as a catalyst. If we have traces of arsenic oxide, the efficiency of the catalyst will decrease. So chemical substances which decreases the efficiency of a catalyst is called as catalytic poison. Some of the examples here are there. All right. So change of temperature alters the rate of catalytic reaction as it does for the same reaction in the absence of catalyst. So change of temperature. When temperature changes, the catalytic reaction rate also changes. So this is important, very important. So this is chemical, this is potential energy. This is the reaction sequence or reaction path. Reaction path, we can call it, or reaction coordinate also, we can call it. So you can see here, this dotted line is in the absence of catalyst. So you can see this is A and B reactant and C and D is a product. Now, in the absence of catalyst, for the reaction has to take place, it requires a lot of energy of activation. ES stands for energy of activation. So if it attains this energy of activation, then the activated complex, uncatalyzed complex is formed, and then it decomposes to give you the product. But when we use the catalyst takes in a different path by reducing the activation energy. To attain this energy, the time required is less. Once it is attained, catalytic complex is formed, and it will decompose to give you the product. So this, they can ask the effect of catalyst on rate of a reaction. You should say 2 or 3 points. That is, in the absence of a catalyst, the amount of energy activation required is more, so that ion catalyst complex is formed, and that will decompose to give product. But in the presence of catalyst, energy of activation is decreased, and the reaction rate takes its different path, and products are formed easily. This is an important question, very important question for 12th standard. Now, next we have theories of catalysis. Theories of catalysis we have, and then we're going to learn some of the questions based on the catalysis in the next class, maybe on Friday, and then we'll go for the topic colloids, right? So theory of catalysis, we will start in the next class. We will stop the class for now. Thank you.
Thank you, sir.